Hi there, welcome back to the new video. Today we'll be exploring the GitHub for sentence transformers, and specifically we'll be looking into the unsupervised ways for training the sentence transformers. I hope we all understand that training a supervised version of your embedding representation for any downstream task, it could be sentence retrieval, semantic similarity, or just as an initializer for any downstream task. You need to curate a training dataset that usually looks like anchor, positive, and negatives. Now it's up to you if you can have both positive and negatives generated, or else you're also good if you have anchors and positives. Now think of anchor as sentence 1 and positive as sentence 2. In this case, this is sentence 1, sentence 2, and sentence 3. Sentence 1 and 2 should be closer to each other, and sentence 1 and 3 should be far from each other. That's how you start annotating this stuff, and that's eventually what the model optimizes on. But again, mining these negative sentences also have their own nuances. You can have like hard negatives, you can have soft negatives, and depending on the use case, a combination of hard and soft might make up a really optimized data set. But what if you don't have these negative samples, right? So we have, let's say, pair, which is A is a sentence 1, B is again sentence 2. In a batch of 4, let's say you have A1, P1, A2, P2, A3, P3, A4, P4. So each of these AIs and PIs are treated as positive pairs, which means in semantic space they should be closer to each other. Now you extrapolate your dataset in the form of saying A1, P1, P2, A1, P1, P3, A1, P1, P4. So these are the three data points that you create and then train your model. Now here A1 and P1 are closer to each other because that is what you already gave while preparing your positive pair dataset. Now P2 here was closer to A2, so we add that as a negative example for A1, so that way we complete our triple. Now this again is sort of an assumption that A1 and A2 should be a little far off, then only P2 can be the negative for A1. So inherently we assume that to be holding true. But yeah, again, creating a positive dataset still requires a lot of effort, right? So it's always good that we look out for unsupervised way of training these models. So this documentation under sentence transformers talks about it. It has a lot of methods, which is CT, CT in bash negatives, MLMs, SimCSE, TSDAE, and query generation. As a part of this video series where I talk about generating unsupervised sentence embeddings, I'll try to cover each of them in their dedicated video. So let's see what we'll be talking about today in this one. Okay, so the first one is TSDAE. So in this video, I'll just be focusing on this method, and the remaining methods will follow with the next videos. Okay, so let's jump onto this paper. So yeah, TSDAE stands for using transformer-based sequential denoising autoencoder for unsupervised sentence embedding learning. This is from researchers from Ubiquitous Knowledge Processing Lab and University of Darmstadt. So with all the motivation that we talked about, why do we need unsupervised way of learning these sentence embeddings? Let's directly jump onto the architecture to what they propose. Yeah, so what they say is we need to have two units of transformer. One will act as decoder, one will act as encoder. The idea is to create a dataset that is noisy, and at output end you want to remove that noise and have non-noisy version of the same sentence generated. So for example, if the sentence is I am a boy, so you could have multiple types of noise injected in this. You could, let's say, shuffle this, am I a boy, boy, I am. So that way you can generate 24 variations of the same sentence. So each of that acts as your input, and on output you try to map it to I am a boy, which was the original sentence from which all these noisy sentences were created. So yeah, at the heart of it, this is what this paper proposes. Now if you remember clearly, there's a paper that's known as BART, which is from Facebook, I believe. I do have a video on this. I'll link that in the I button and description. Make sure to check that out as well. But there also the idea was similar, wherein you add multiple types of noises such as swapping, deletion, rearrangement, and maybe a few more to the input sequence, and at output you would expect the model to kind of get you the original denoised sentence. So yeah, it's again in the similar lines. So now that's how you train the model. And once it's done, and at inference, what you do is you trim off the decoder from this and just use the encoder part to encode any sequence that you now want to evaluate. So which means during this entire training, the representation that you get out of this pooling layer is the bottleneck, and this is what the model has to put its focus on to make this as much robust as possible, because if this has any kind of loss, then that goes to decoder, which will then allow model to not remove all the noises. So the model during its iterations tries to make pooling layer as solid as possible. Okay, so let's see if they have any questions. Yeah, so this is how or essentially what the model tries to optimize. Here X bar is nothing but the noisy sentence and X is the non-noisy version of the same sentence. So given your noisy version, you want to maximize the generation for all the tokens that you see in the non-noisy sequence. And that happens for every word. And this opens up to nothing but a softmax in the time sequence over the entire vocabulary. Okay. Yeah, so they had 2 pointers specifically written. So the first one is, they say that the decoder decodes only from the fixed size sentence representation produced by the encoder. It does not have access to all the contextualized word embeddings from the encoder. This modification introduces a bottleneck that should force the encoder to produce a meaningful sentence representation. So I'm not sure if how many of you remember, but in traditional encoder-decoder transformer architecture that was proposed in Attention is All You Need paper, we'll have your encoder block, you'll have your decoder block. Here is where your words go and you get their contextualized representation as an output. And this is where, let's say, your beginning of sequence starts. Now what goes into the decoder is the representation for this along with the encoder-decoder, each of the learned encoder representation, which means this acts as your query. Then you have key value pair for each of these words. And you calculate the contextualized representation as Q into K, do a softmax, do a normalize into V. So this is for W1, similarly for W2, and you take a linear combination of this. And this is what is a hidden representation that goes along with BOS. And then you decode output word 1. And the same process is continued for the remaining sequence. But what they say over here is like they don't follow this scheme. Instead, they use the pooling representation or the CLS representation as a fixed vector that kind of represents all the information that is there on the encoder side, and use this along with BOS to start decoding your O1s till whatever your output sequence length is. Forces your model to have really good representation over here, because that's the only thing now each of the words are going to see, and put their implicit attention on its bits and pieces rather than getting exposed to all the words that were there in the input sequence. So yeah, that's one change that they do. The second is this one, where they say the model architecture of TSDAE is a modified encoder-decoder transformer where the key and value of cross attention are both confined to a sentence embedding only. Formally, the formulation for this modified cross attention is this. Okay, so you have query, key, value. Now if the query is your current hidden word representation, then you're just calculating attention for the sentence embedding that comes part of your CLS. So I've already discussed it over here while discussing this figure. But yeah, that's exactly what's written. You have key is also your sentence embedding, V is also your sentence embedding. Now this is different from the traditional one because there every word will have its key value pair. So that gets inserted over here in a traditional sense. Okay, so yeah, I think we're done with the paper, and this is what this paper proposes. For the next video, I'll be touching on the paper that is titled as SimCSE. So make sure to subscribe to the channel and hit the bell icon to not miss out on any notifications. Also do share it with your friends to whosoever you think might be interested in this content. I'll meet you in the next one. Bye bye and take care.